answer before the. I think this is a very interesting question. So suppose consider the quadratic equation x root 8.
X root 8. Okay. X root 8.
Yes, sir. Plus 1 over x root 8 is equal to root 8.
Okay.
So we have that this solution has two roots, x1 and x2, both real roots belonging to R. So two roots belonging to R. So the question now is, if the 1996th digit in the decimal expansion of x1 is 6,
Is in decimal expansion of x1 is 6. Okay.
then what is the 1996th digit in the decimal expansion of x2? We need to find that.
Okay. Then 1996th digit in decimal expansion of.
Yes, sir. I got the answer, but I'm not satisfied with how I got it, sir.
Okay, then please
Like,
tell me how you got it. That is very important.
yes, sir. So we'll solve this quadratic equation first. We'll put it in standard form. Take x root 8 denominator. So it'll be 8x squared plus 1 is equal to root 8. Yes.
Is this correct?
So I'm getting 8x squared plus 1 is equal to 8x. So the root 8 will.
Yes. So no. So there will be no root 8 in the end. Yeah.
Yeah, no root 8. 8x squared minus 8x plus 1 is equal to 0. So x will be 8 plus or minus root 64 minus 32 by 2 into 16. So half plus or minus root
Half.
32.
Half like this.
Yes, sir. Yes, sir. I just took the 8 over 16.
Okay.
Half plus or minus root 32. We can simplify that.
Yeah. Yeah. Root 2 by 4 will. Is that correct?
Yeah, one second. So root 32 root 2 squared into 2 cubed.
Yeah, this is 4 root 2, right? 32
Yes,
is
sir.
4 root 2. So that's root 2 by 4. Is it?
Yes, sir. Root 2 by 4.
Okay.
So now we don't know what x1 is. We don't know what x2 is. But one thing we can definitely say is x1 plus x2 is equal to 1.
X1 times x1 plus x2 is 1.
Yes, sir.
It's not
So
equal.
So now the weird thing, the one we write it as 0.9 recurring.
Okay. You write it as 0.99.
Yes, sir.
Okay.
So then we can see that in the decimal expansion, the corresponding digits should add up to 9.
Yes.
So then the 1996 digit will be 3.
Yeah. So, yeah. That's perfect, right? Like, yeah. That's a very
So,
nice.
but this 0.99 thing, it's a bit, it's correct. Like, I know that logically it follows, but
Yes.
then the thing happens is, what happens if we just write it as 1.0 recurring?
Yeah, so if you write it like this, see, both are equivalent, both are equal.
Yes.
I mean that both represent the same number.
Yes, sir.
But one of them is more convenient for your problem, so you use that. That is all,
Yeah, okay. Yes, sir.
right?
So, okay, I see. I
Maybe
mean,
there is
they're both
still,
equal to 1.
huh? Yes, I think, no, it is fine.
Yes, sir.
I think it is fine
Yeah,
because,
then that
uh-huh,
wraps up the problem.
sorry, yeah, that does the problem, right? Like, see, the question
Yes,
is also very clear because if someone says that the 1996 digit contains 6, it means that the number has a unique decimal expansion.
correct. Yes, sir.
Because see, not every number has a unique decimal expansion,
Okay.
right? Like the one you took here,
Yeah, 1.
right? Yeah, one has this 0.99. So, but which numbers don't have a unique decimal expansion? Precisely those
Numbers
in
that
which,
don't have one, that don't have a proper decimal, like irrational numbers.
no, but no, irrational numbers have a unique decimal expansion.
Yeah, yes, sir. That's what.
Yeah,
Numbers
but
that don't have a terminating decimal expansion
no, I'm not
have a
interested in
unique
that.
decimal.
Uh, that don't have yes, that is correct. But
Yes.
but but numbers that have a unique decimal expansion are a proper subset of that,
Yeah, correct. Yes, sir.
right?
Okay.
So
Huh.
that's the kind of thing. But what I'm saying is that the numbers that don't have a unique decimal expansion are only those numbers which eventually have 999s. Okay.
Okay.
Now that if you want to take that as a homework, you can prove. So find all numbers which don't have a unique decimal expansion.
So isn't it all rational numbers?
No, because there are many rational
So,
numbers which have a unique. Okay, so tell me. Okay, maybe you are right, but let's talk about this.
uh,
No. So wait. What about 0.5? I think you are correct.
0.49 bar.
Right. So that's something that I'm missing. Yes.
Yes.
Right. And
Or 0, we can write it as 0.50 bar.
yes, this is correct. Okay, so you are saying that all no, but then what about this thing?
Even I was thinking of same number. Yeah,
Yes.
correct,
So I
sir.
think I think what you are saying is correct. Like exactly. So okay, so let's write it. Unique. So you are saying that unique decimal expansion is if and only if non-terminating.
Yes, sir.
If and only if and only if there is a non-terminating decimal expansion.
Yeah.
No.
Yes, sir.
Yes, yeah. If and only if non-terminating decimal. Yeah, and I think this is precisely correct, right? But then obviously
Yes.
it's not a proof. You have to prove it. If you want to
We have
prove
to
this, you
prove.
can try to prove it.
I'll
Okay.
try it, sir.
So
For
you have to just
simplicity, I'll just work in base 10.
yes, base 10 only. Yeah. I
Okay.
mean
Yes.
other bases will probably be equally simple. Okay. But
Yes.
yeah, just maybe slightly new. Anyways, so yeah, and these numbers I think which have a unique decimal expansion are called normal numbers or something like that.
Oh,
Yeah,
okay.
you
I
can, if
didn't.
you want, you can read about it. There is a
Yes.
lot of probability theory that is done in that, in normal numbers. Okay.
Okay.
But
Yes.
probably in, yeah, like if you Google normal numbers, you probably see some lot of probability theory also.
Yes.
Anyways, um,
Oh,
yeah,
yes. So one more interesting question.
huh,
Like, it's not a contest question or anything. I just came up with it. So suppose,
okay,
so we consider C sub 10. So I don't know how to spell how to pronounce it, but it's Champernowne's constant in base 10.
hmm,
ChampernownE.
okay,
Yeah. Champernowne's constant in base 10.
huh,
So, sir, it's zero. It's equal to 0.1234567 8. We go like that, concatenating all the natural numbers.
okay,
So my first goal was to prove that this is irrational. We know that it's non-terminating because infinitely many natural numbers,
mm-hmm,
and we also know that we can find a string. string of zeros of any length. Suppose we find a string of zeros of length n,
Hmm.
then we can find a string of zeros of length n plus 1. So it can't be repeated.
No, no. Okay, so you want to show that it is irrational.
Yes, show that it is irrational.
And then what you're saying later is if is an argument for that.
Yes, sir.
Okay, so what is the argument? String of
So
zeros.
first we prove that it's non-terminating, which is easy.
It is not terminating, right?
Then to prove that it's non-repeating,
Huh.
what we can do is we can find a string, consecutive string of zeros. So suppose 100 appears in this
Ah,
100.
yes, yes.
100 appears, but then somewhere in the decimal expansion 1000 will also appear.
Okay,
So it definitely can't be what is that, repeating. We can't have a repeating block.
but so suppose you have a repeating block,
Yes, sir.
uh, but uh, but why should that repeating block contain 100?
Okay. If it doesn't contain 100, then we can generalize it to any digit. Like we'll have one, we'll have one in there. It has to contain one at least, the
Okay,
repeating block.
okay.
Then we can find 11, those two ones.
No,
And then
but why
after
will there
11,
be 11 in the repeating block?
okay.
Okay, let us if you say that like your pattern starts from the beginning or something,
Yes, sir.
but the point is that the pattern did not start from the beginning, right?
Okay. So suppose it starts somewhere else then.
Huh. Um,
So that's what. So we can show that the length of the string is unbounded. So it definitely can't have a finite length.
so how do you show that? Suppose it starts from the kth position.
Yeah, suppose it starts from the kth position and ends at the k plus mth position.
Okay.
So this so suppose this is our repeating string, sir. So
Huh.
what we're saying is everything that comes after this is of the same, like the same
Yes.
uh
Yes.
string. So now, so what I took was I just supposed it starts at 45, and the
Okay.
next is definitely not 45. It's 6, 7. So like that,
45 like this. 46.
yes, yes, no, sir, no, sir. I just suppose that 45 is the block,
Uh,
simply just as an example.
no, you mean case
And
45?
yes, a k is 45 and k plus, no, k is 4, sir.
Okay, case 4.
And then k
K.
plus m,
Huh.
n is 1.
No,
I
I
just
am
took that case.
okay. So K is 4 and M is 1. Okay.
Yes, sir.
Okay. So K is 4 and M is 1. All right.
So then we'll get that the block is just 45. We can easily show that 45 is not like it's not the correct block because we get a contradiction. We get 67 is equal to 45.
Yes.
So, I was thinking somehow we could generalize this.
Right. Right. So how do we generalize it?
So suppose we have this block, sir, and if we have that it's repeating,
Hmm.
then it means that this entire repeating block is also a natural number because that's from the definition of our constant.
The entire repeating block is a natural number.
Yes, sir, because that's the definition of our constant. We are concatenating just natural numbers. So if this repeating
Okay.
block appears,
Uh-huh.
if this repeating block appears,
Uh-huh.
then it has to be a natural number. But then it's
Yes.
repeating infinitely many times.
Huh.
So it's a natural number with infinitely many digits, which cannot be the case.
Uh-huh. No, sorry, I did not understand. So if this is this block is a natural number n,
No, so I'm saying, correct. Okay, okay, yes, I
hmm,
think. Oh,
then the next block is also n, and you want to show that cannot happen.
okay, so can we show that we can never get n plus one in this fashion?
Uh-huh. But then what will that show if you cannot get n plus
Oh,
1?
oh, correct, correct. Yes, sir.
Like, I understand it is clearly irrational, but the
Yes,
argument
clearly
is
is.
not yet, yeah, in place.
Yeah,
Let us think about it.
yes, sir. So it starts at the kth, k plus m. So we'll have m plus 1 digits, no, sir, in this repeating block that we consider.
Right.
Okay, so uh, so
Hmm.
maybe
Yeah, I think it is easy if we just formulate. So, see, like the way I can say maybe is that let us say it is starting at the kth position and it stands at k plus 1th position, and then you can say, okay, look at the largest consecutive sub block of zeros in this.
huh.
Okay,
Yes, sir.
it could be it's possible that there are no zeros in this also. Okay,
Yes, sir.
so you look at the largest block of zeros. Let us say that is some size L
Yes, sir.
in this. Okay, now if these are all zeros, then you will
Yes,
clearly
sir.
get a contradiction because
Okay, yes.
then because then it means that everything after this is zero, right?
Yeah.
So all are not zeros. Now if there is so it means that L is strictly less than m plus 1. Okay,
Yes.
and but then as you were saying, right, there is a natural number with, let's say, 2m zeros consecutively, right?
Correct.
And that natural number will occupy an entire block at least at some stage,
Which
like whenever.
which gives us the contradiction.
Yes, so it's just a way to say it clear properly, that's all.
Yes.
Yeah, the
Yes, sir.
idea is there, but yeah, that's all I will
Yes.
say. No, not yeah, now you can just imagine that you were almost there, right? It was. But so how did you start to say by the 10? So like where was your argument not?
I
So
think like that's what, so like you said, the idea was there, but like I couldn't formalize it like this. This L is
yes,
less than m plus one, and
ha
then
ha.
to show that eventually you'll have so many zeros, and 2m can never be greater than m plus one, like that.
Yes, yeah. So the block size, that the block size is same and those kind of
Yes, sir.
things. Yes, but what exactly were you saying in the beginning? Uh,
Yes, sir. So this was the first part. Like I was just thinking of this concept. Second part is,
okay.
suppose we truncate this expansion only at natural numbers. So 0.12345 is a valid truncation.
Okay. No,
0.1,
truncated at natural numbers means that
yeah, that's what's a. So suppose 0.12345678910. That is valid, but 101 is not valid.
okay. So truncate C10 at natural numbers.
Yes, sir.
Okay.
And we call the length of the truncation, we define the length of the truncation as number of decimal places in the expansion.
Okay, that is fine. Okay.
And then so the question is, what values can this length take? It can take any value from 1 to 9, but it can't take 10.
Huh, okay. But that is
After
just a
1
matter
to,
of counting the number of digits, right?
yes, so
So,
counting the number of digits. So
yeah.
my question is like, suppose we truncate it at the kth natural number, then what is the length?
Yes. So you have to just count how many digits you use when you write numbers from 1 to k.
Yes, sir. That's what I was
Yeah.
thinking too.
So you can, I mean, you cannot answer this question without having another parameter, in the sense that without saying that, okay, let's say that k has this many digits.
Yes, sir. What I did was I bounded k between 10 power m and 10 power m plus 1 for some
Yes.
m.
Yes.
And then I found a formula.
Yes, that I think that is all you can do, because without
Yes,
knowing between which, because our notion of digits is based on powers of 10, right?
parts of
So
that. Yes,
without introducing this with this parameter, you cannot really answer that question. And once you have this
correct.
parameter in the question, then the answer is trivial, right? So
Yeah, yes, sir.
yeah.
And one more interesting thing I was considering is, what is the kth digit in the decimal expansion of this? Which I
Uh,
think
uh-huh.
from this, again, so I think we're given k, so we know between what parts of 10 it is. So can we like do something with that?
But now you're saying the kth digit. What is the case? I'm
Kth
erasing
digit.
this one. Yeah. What
Okay,
is
yeah,
the
kth digit.
kth digit? That may be, I don't know if that is.
I actually looked it up online. So this same question, what is the
Uh-huh.
kth digit of C10? It appeared as a question in Project Euler, which is a coding competition. And like they gave code to find the kth digit. But as a formula, I don't think anyone. I don't think it's on the internet.
Okay, okay. Yeah.
Mm.
So kth digit would mean that, yeah, it I mean, because see, the formula might be, because if it's your own question, right? And the formula
Yes, sir.
might be extremely messy. I don't know if there is a good formula.
Correct. Even I don't know. I don't know if anyone's found a formula yet.
Yeah, but the no, it's not like has anyone found. Maybe is anyone interested in finding the formula?
Yeah. Is
It
anyone interested?
in
Yeah.
not in the that yeah, you understand, like the formula may not lend any insights into this number or anything.
Yes. Sir.
Okay.
Yes. Sir.
um yeah, Arithya, just one minute. Okay, we'll just start.
No,
Okay.
no, I'll
Good morning.
join in some time. Okay. Yeah, I just wanted to let you know I'm joining in
Yeah.
some time.
You can just wait. We'll finish in 1 minute if you want.
No, I have work, so I'll finish that and I'll join in some
Oh,
time.
okay, okay, sure. Yeah. Uh, so the kth digit. Yeah, I don't.
Another interesting factor, it's been proven that this number is transcendental.
Oh, then you should. Okay, okay. Hi, Arithya, are you
I
here?
think,
Maybe you can ask her. Yeah, she knows a bit of number theory.
oh,
Yeah, okay.
I think she left to do that
Ha, ha,
work
ha.
or something.
Transcendental. I will not be able to prove, obviously. Uh,
Yes, sir. But I think this was one of the first constructed, like it was made for the purpose to be transcendental. I think this number.
something like
I
that.
remember reading somewhere. Yes, sir.
Okay, okay. Yeah.
Another number that was made to be transcendental is the Liouville's constant. So it'll go 0.10
Uh-huh.
1
Yeah,
triple zero
I
one
know of
four
that
zeros.
one. Yes, Loiva's
Yes.
constant and I think,
These were
yeah,
yes, sir.
I
These were
saw one.
constructed just to be transcendental.
Yes, yes, yeah. So, and it is not difficult to actually prove the it is transcendental. No, but it's not elementary completely.
Yeah, yes, sir.
Like there are some ways. Uh, yeah. Basically, we say that like every rational, like every number which is not transcendental, which is like algebraic. Okay.
Yes,
So algebraic numbers can be approximated. So every number can be approximated by rationals, right?
yes, sir.
But how well can you approximate? Okay, a
Okay.
rational
How
number.
close you can get?
Yeah, yeah, yeah. How, no, I mean, not just that, because see, if you take any number x, okay,
Yes, sir.
uh, if you take any number x, then you can obviously find a rational number which will, you know, and for any epsilon, you can do this, right?
Right. Yes,
Right.
sir.
But if you take now, a point is that suppose you take 1 by n, right? Then
Hmm.
how like like you want to find a rational number such that this will happen, and the qn should not be very large,
Okay.
right?
So
So
I
that is,
yes, without that restriction, we can get arbitrarily close.
yeah, you can get arbitrarily close, but let's say that you want this degree of closeness 1 by n. Okay,
Okay.
then like how large a qn do you need? Okay, so yeah, so that kind of thing. And the thing is that the larger the qn you need, then it is like not a good means, you know, like the approximation is said to be better if you can do it with smaller qns.
Smaller QNs. So suppose
Yeah.
if QN is 1, then
The- like that is too
uh
much in that sense, right? One is too
huh,
much to
correct.
ask, right? Where the qn will be a function of n, obviously. Like see, if you
Yes.
keep increasing this n, the qn has to keep you cannot say that I will keep qn up till 100 and I can approximate. You cannot do it, right? So if you
Yes,
say
sir.
that I will keep qn to less than 100, then for some n you are bound to fail,
Correct. Yes, sir.
right? Yeah, because you kind of get only finitely many numbers if you keep qn to be less than 100, and the values of pn cannot vary too much, right? And they have
Correct.
to be
Yes,
close,
sir.
so that will not work. So qn has to certainly get larger and larger, but like something like, you know, qn, can you make qn less than 10 to the power n or something like that, right, as a function, right?
Okay.
So
Like that.
yeah, right. And then what happens is that if x is transcendental, then kind of such bounds exist. Okay.
Okay. If it's transcendental.
Yes, or maybe it's the other way, that I mean, if it is not yes, yeah, I think it's like that. If it's transcendental, then they can be better approximated.
Okay.
You understand, right? So like transcendentals are more mixed. Like it's
Yeah.
something like, you know, the irrational numbers still have some distance, and algebraic numbers are still at some distance from the so I'm saying that the like you take the algebraic numbers which are irrationals, right, and you can approximate them with rationals, but they are also like rationals. They're still, you know, closer to rationals than transcendentals
Closer to rational. Yes, sir.
in features, right? And hence on the number line they are a little apart.
Okay.
You see that thing, right? Like two natural numbers are,
Huh.
all the natural numbers are like similar, same feature numbers, and they come with some gaps, right? And then you
Yes,
look at
sir.
all the numbers with, let's say, end with a 0.5, they will also come with kind of some,
They
you
come
know,
with that gap, that
kind
length
of
one.
yeah, gap or some length, like, so basically the numbers with a similar feature are somewhat, because you have to scatter them, right, to make it up. Right.
Yes, sir.
So numbers with a similar feature still come with some gap, and so the algebraic numbers are somewhat more like rational numbers, so they still come with some gap, right? So
Hmm.
so with them you cannot expect such a bound. Yeah.
Okay.
But the transcendental numbers are completely different. They're like living in a new different dimension. in the sense that
Huh.
they are on the number line
That's why
only, but there's some mixed, like, yeah. So there's some, so they're
they're
like very,
transcending.
yes, so in the sense that they are very close to rationals, but they are not rationals. And such thing will then be very badly rational, very badly irrational.
Yes, sir.
You understand? And so for them, such bounds exist. And then you show that for things like Liouville numbers, this bound, or maybe such bounds exist. So if you want to show that something is transcendental, then maybe you have to show that for something which is algebraic, such bounds don't exist, or such some things are like that. Okay, it's like
Okay.
this. And then you show that for Liouville numbers, uh, this is not like that. Okay, for Liouville number, you can do it like this, and then it cannot be algebraic.
Correct. Yes,
Okay,
sir.
so it is, so you study some property of algebraic numbers, and then you show that that property is violated, and so it cannot be algebraic. And it's
Algebra.
not. This
Yes,
is
sir.
the topic of what is called Diophantine approximation.
Okay. I'd
So
heard of that, but
yes,
I
it
didn't
is.
know that.
Yes, it is a very interesting topic which I don't know much about. I don't know. I have not studied that at all. So yeah, this kth digit. It seems like a messy question. I don't know if this is an interesting question.
Yes, sir.
Yeah. So because because see, you know what natural numbers, no, so what lengths can be taken, right?
Yeah. We
And
know the lens.
yeah, what are the possible lengths? uh, no, but that is when you truncate at natural numbers. Yeah.
Correct. Yes.
So yeah, so maybe you look at the closest length that you get when you truncate at natural numbers, which is closest to k.
Yeah. And then
Yeah.
maybe see what digits are in that
Yeah.
neighborhood or something like that.
Yes, yeah. So like this is maybe Sn. So when you truncate at the nth number, and then you get this, and you know this length L. And then
Yes.
you are starting with some natural numbers. And then you can maybe do some counting. I don't know this. Yeah. Yeah.
Yes, sir.
Okay.
So
So
one last thing, sir.
uh,
There was this competition in ISI.
uh-huh.
So it was an exam kind of thing that's going to be held in January, and
Hmm.
it lets you attend their summer camp. I signed up for it,
Yes, do the
but
case.
then
Huh?
I forgot the name, sir. Do you know what the name of the competition is?
I The whole thing I think is called integration.
Integration, yes, sir.
Yes.
But
So
I
uh-huh.
signed up for it and I saw a few sample papers as well, but now I can't find it on the web for some reason. I'm looking up ISI integration summit and all of that.
Okay,
For
okay.
some reason I can't find
I
it.
mean, I can ask the people. Yeah, integration, ISI. Yeah, even I have the Excel document also, because I'm in ISI, so
Huh.
they send the mails. But uh,
Okay.
yeah, but yeah, this is integration 2023.
Integrate. Okay, yes, sir.
Yeah. So
I'll
about the
I'll
exam, you're
just
saying, right? They have an exam also. Yeah, so I will
yes, sir,
I will
it's
let you know. So
exam.
this is, I think, this one, but I will send you a proper link where you can find the paper and so on. Yeah, these
Okay.
things are these things. Huh? Anyways, I will send it to you. Okay.
Okay, sir. Okay,
Later
sir.
on, I'll send it to you. This is a good exam. You should write it. Okay.
Yes, sir. I
Even there is
signed
a
up for it.
CMI stems. I don't know if you have written it earlier.
Tesla, yes, the CMI
Castellate.
test late. I got the link, sir, but the thing is, on the day of the exam, I have my Sahodya pre-board.
Oh, okay. Then maybe, yeah, then you are not right. So then there is no question.
Yes,
So you can leave it. Yeah. Okay. All
yes, sir.
right then. We'll see you next Sunday.
Yes, sir. Next
Yeah.
Sunday, sir.
Okay. Okay.
Yes, sir.
All
Thank you,
right.
sir.
Okay.
I'll
So
leave the class.
New Year is when, on the first?
Yes,
I mean,
sir.
yeah,
It
it's
does.
always on the first, but
It's
is
on
it?
the first.
Oh, but it's also a Sunday. Otherwise, we could have. So, is your college closed now, because we have missed a lot of classes?
Yes, sir. The college is closed till 4th. After which, on 4th, the first Sahodya pre-board starts.
Oh, okay, okay. Okay,
So
okay
I'll be
then.
able to join on first.
Let's do it on first then. All right.
Okay.
Okay, take care.
All right. Yes, sir. Thank you, sir.
Thank you. Yes. So, hi, are you here? Mm, okay, let us see. Oh, yes, you're here. Okay. Yes, yes. Sorry for being a little late. I'll just drink some water and come. Okay. Yeah, just 1 second. I'll also bring my book. Yes. Okay, so let us start. Um, yeah. So yes. So we were looking at the radical. I'll continue to.
Today, were you not supposed to present that injective theorem? Like every R module injects something.
Oh, should we do try to do that, or should I continue with the one that I was doing last time?
So we had an incomplete proof on that the left radical. So if you start that from the beginning, it would be great. And then you finish that, and then we can.
So
Yeah,
let's finish
then
that
first,
one. Yeah. So the meeting
then
is
we will
going to end. So let's finish that one, and then we can.
because we
Yeah.
only have 40 minutes here.
Okay, no problem. I can go for an hour. I don't have a problem. But it's yeah.
Yeah,
Okay, no problem. Let's see. So we can only do till 40 minutes. Not a problem. But let's join again, and then I'll try to start with the proof of that.